So, hello dear students, I welcome all of you again. So, please mark your attendance, write your name and roll number in the comment box. So, let the other students join us, then we will start our lecture within 1 or 2 minutes. So, in our previous lecture, which was not successful due to some trouble in streaming, actually I moved from one place to another place and there is some sort of connection problem. So what we are talking in our previous lecture, we are talking about the specification of states in a system, and we have talked about the classical specification of state and quantum specification of state. And generally in that I have described that in quantum mechanically we describe a system with a wave function. So quantum mechanically, so we will talk in detail about these topics. So we will describe a system, so which is having a large number of particles, and we will study the wave function of those particles in order to explain their position and momentum. So it is something like q1, q2, q up to f, and similarly p1, p2 up to pf. So where f is representing the number of degrees of freedom, and this is for one system. And similarly, if there are large number of systems which are present, so that is having the mental copies, so which we call as the ensemble. So then we will explain about the wave function of each system, and then we will collectively calculate the statistical distribution of these particles. And suppose if there are n number of systems, so and if we have, so the total wave function that we will generally consider as the number of degrees of freedom, so that comes out to be n into f. So the system, so the atoms and molecules, so they are properly described, so though not perfectly in terms of quantum mechanics. So let us discuss the picture of classical specification and quantum specification, so of a system in a state. So first of all we will talk about the classical specification of state. So let us consider we have a large scale park. So something like this. So this is representing Q versus P, that is the area of that park. And let us consider a person. So it is walking in this park, and we are viewing this person from some particular height. So let us say we are viewing this person from a height that is of the order of 5 kilometers from above the earth. So when we are looking this person from a height, so this person will look like a particle. Now if this person, he starts to move here and there in the park, so if we take a picture of this person at particular instant of time, so if person is moving or person is walking, and we take a picture of this person at particular instant of time. Now, according to classical mechanics, we can predict his position and we can also predict his velocity. So from that pic, we can predict his position and velocity. And from that velocity, we can predict his momentum. So that is of the order of p, which is m into v. So consequently, we have with us his position and momentum coordinates. So now if there is a large number of persons, or you can say there are large number of particles, so which are present in that particular space, then there can be a large number of coordinate points so present in that space. So similarly, if there are large number of points in the park, so we can see those points classically, and therefore there exists a very large number of coordinate points in that plane. So something like this, suppose this is the place, so that I generally defined as the park, and so if there are large number of persons, so each person it is representing a point distribution, and there are a very large number of coordinates, and each coordinate it is representing a particular momentum and particular position coordinate. So we can denote it as pi and qi. So in this example, so this park is considered as a phase space, and this person is considered as a coordinate point. So similarly, so when we are talking about any sort of matter which is present in a particular system, so that matter, it can be a gas, it can be a liquid. Now this gas, it is having large number of atoms and molecules, and similarly these free moving atoms and molecules within the system, so we can explain or we can describe their position coordinates and their momentum coordinates at a particular instant of time. So this is how from these position and momentum coordinate we can put these coordinates in order to derive the equation of motion, and from equation of motion we can further calculate various thermodynamic parameters. So this is how we move in classical mechanics. So here I would like to explain one important point. So generally there is a question why we take momentum and not velocity in the phase space. So generally respect to position coordinate at a particular instant of time, not velocity. Now here if we have a system, so in that system if the particles, so they are moving very fast, so particle velocity is very high, so that is the velocity which is of the order of speed of light. So in that case, so we have to consider the relativistic regime. So because we all know when the particle it is moving at a very high speed, that is of the order of speed of light, and at that time the mass of the particle, it gets changed from m naught over 1 minus v square over c square. So as all these particles now which are present within that system, so they are moving at a very high speed, so there is change in mass for each particle. So that's why when there is a change in mass, so we generally, in order to consider the exact values, so we generally consider, or we generally calculate the momentum coordinate of those particles, so rather than only the velocity. So for the exact calculations, so in the relativistic regime or in general, we generally calculate the momentum coordinates of the particle in the phase space rather than velocity. Now, so phase space, it is a very complicated and is difficult to tackle with the phase space. Now if we consider the same person, so in our previous example we are talking about the person which is moving in a plane, so that is along the xy plane, so that is having 2 degrees of freedom. Now if we are considering the person, it is flying in air, so instead of roaming in the park, then we will generally consider the phase space as the volume of the park, so within which region that person it is moving, and that is our 3 degrees of freedom. So that is 3-dimensional system, so which is having 3 degrees of freedom. So we have to calculate the position of that flying particle or that flying person along x, y and z coordinates. So the large number of points in that volume, so that is generally, so the value of this phase space, it is dependent upon the degrees of freedom, so in which we are talking about. So if there are 2 degrees of freedom, so then we generally represents the momentum coordinate as px, py and position coordinate as qx, qy, and if it is having 3 degrees of freedom, so for each particle we have to calculate, so the momentum that is along the 3 axes, and similarly the position along the 3 axes, so that is generally the 6 and degrees of freedom of the phase space. So 6n represents, so 3n of position coordinate and 3n of momentum coordinate. So specification of P and Q is equivalent to specifying a point in 2 or 3-dimensional space, which is called the phase space. Now this particle, as this particle, it is moving along a particular position and it is changing its position with respect to time. So we will trace out that particle, so how it is moving within that confined volume and how it is changing its position and momentum with respect to time, and that we will draw out a trajectory. So that is known as the elliptical trajectory, which will provide out the information about the position and momentum coordinates of those particles which are moving in that phase space. So generally, in order to calculate the exact position of that particle at a particular instant of time, or in order to calculate the exact momentum and how it is changing with respect to position, so we generally divide these position and momentum coordinates, so in small fragments, so in small cells, so which are generally known as the grid cells, and each grid cell that is of equal size and shape, we can study the statistical distribution, so how the position of these particle it is being changed, so for a very infinitely small interval of the change in those coordinates. So this particular one cell, so that is dq and dp, so this is known as the one grid cell, so that is having the change in position coordinate of the order of dq, and similarly, so I will change the color. So this is known as dp, that is the change in momentum. So in order to get the situation in the countable state of the system, so we will subdivide the range of this position and momentum coordinates into very small interval. So here we have considered dq and dp be the length and breadth of the two dimensional corresponding cell in a plane, and the area of this plane. So generally for a two-dimensional system we will calculate the area, and for a three-dimensional system we will generally calculate the volume of that cell. So for this plane we will calculate the area of this 2D system, so that is dq into dp, that is of the order of h naught. So this will provide out so the information about the distribution of these particles, how many particles so which are present and what is their change in position and momentum coordinate, and you can calculate the unit. So this is momentum mv, and the changing position with respect to r, so mvr. So this h naught, it is representing the unit of angular momentum. So that is explaining that motion of a particle in a particular elliptical trajectory. So that particles, so which are moving in a circular motion. So for a represented, for a cell, we represent which with q and p. So this q and p represents a point between the interval. So it represents a point between the intervals q and q plus dp, and similarly the momentum between the interval p and p plus dp. So therefore the state of a system, it can be specified by the coordinates q and p. So this state generally that is known as the classical state of a system. Now how it is different from the quantum mechanical states. So these in classical mechanics, so these small cells, they can be made too small as possible, but in quantum mechanics, which does not allow us to get these cells as per our convenience, because of the limit of uncertainty principle. So according to this uncertainty principles, the only possible values of this dp and dq, so that is of the order of sigma p, sigma q, So it should be greater than or equal to h by e over 2. So as classical mechanics said that we can see very small cells in the phase space, while the quantum mechanics it restrict the volume of the cells. So in quantum mechanics we can form cells only greater than the order of h bar, so which is the semi-classical concept. So let us compile this in a form. So quantum mechanics ਚ ਆਪਾਂ ਸੈੱਲ ਦੀ ਡਾਈਮੈਂਸ਼ਨ ਜਿਹੜੀ ਆ ਉਹਨਾਂ ਨੂੰ ਰਿਸਟ੍ਰਿਕਟ ਕਰ ਦਿੱਤਾ ਹੈ, ਬਟ ਇਨ ਕਲਾਸੀਕਲ ਮਕੈਨਿਕਸ ਉਹਦੇ ਵਿੱਚ ਜਿਹੜੀ ਆ ਕੋਈ ਵੀ ਰਿਸਟ੍ਰਿਕਸ਼ਨ ਨਹੀਂ ਲੱਗਦੀ, ਕਿਉਂਕਿ ਕਲਾਸੀਕਲ ਮਕੈਨਿਕਸ ਦੇ ਵਿੱਚ ਜਿਹੜਾ ਅਨਸਰਟਨਟੀ ਪ੍ਰਿੰਸੀਪਲ ਆ ਸੋ ਇੰਪਲੀਮੈਂਟ ਨਹੀਂ ਹੁੰਦਾ. ਸੋ ਦੀ ਰਿਪਰੈਜ਼ੈਂਟੇਸ਼ਨ ਆਫ ਦਿਸ dp and dq, so this we can write out as h naught. So here h naught can be infinitely small. So this is classical mechanics, while in quantum mechanics, so the cell it should be of the order of greater than h by over 2. So here h naught is restricted. So this is the representation of the phase space in classical mechanics and in quantum mechanics. Now in our statistical mechanics, if we are having a large number of particles, so we represent the microstate of classical system can be defined by specifying instantaneous position and momentum of all particles which are constituting this system. So once we study out the position and momentum coordinates of a particular system, from that we can extract out the microstate of those classical system, and from those microstates we can find out the various thermodynamic parameters so which will provide us a large information what is happening within that system at a particular instant of time. So we can calculate the entropy of that system, we can calculate the temperature of that system, we can calculate pressure, we can calculate internal energy, Helmholtz energy, Gibbs energy, chemical potential. So there are a large information, thermodynamic information we can calculate. So once we will find out the microstates of the system from this position and momentum coordinates. So let us talk in more detail. So let number of particles which are present in this system, that is equal to n. So for defining a macrostate, so let Q1, Q2, so up to Q3n, it represents the position coordinates, and P1, P2 up to P3n, So this represents the momentum coordinates. So this set of coordinates, so that is the particular value of position at a particular instant of time. So where this I, it can have any value which vary from up to n, 3n. So if we are talking about the three-dimensional system, so the set of coordinates pi, qi, so they may be regarded as, may be considered as particular microstate of a given system. So that is in the 6n dimensional phase space. So this 6n dimensional space is generally known as the phase space, and the point which are present, so there are I points, so these points, they are known as the representative points of this given system. Now this qi and pi, so they are basically the functions of time, because they are dependent upon time, and the value of this p and q, it is changing with respect to time as the particles they are moving. So the manner in which they are changing their position with the time, so we can calculate so the position and momentum with respect to time from the canonical equations of motion. So the value of qi dot, so that is the change in position with respect to time, so that is equal to qh over qpi, and the momentum, change in momentum, rate of change of momentum, so that is minus curly h over curly qi. So these two are known as the canonical equations of motion. So which are representing how the position and momentum coordinates, so they are changing with the time. So here the h, that is the Hamiltonian or the total energy of the system, so it is also dependent upon the position and momentum coordinates. So this is the Hamiltonian of system. Now these set of coordinates, so they also define the microstates of this system. Now as time passes, the value of this pi and qi, so it undergo a continual change. So our representative points in the phase space, it will curves out a trajectory. So let us say this is our 3n dimensional space, and so it will curve out a trajectory how the particles, so they are moving within that system. So this will cause out a trajectory whose direction at any time, it is determined by the velocity vector. So the position of a particular point, so that we can calculate from the velocity vector. So the velocity vector, it is also dependent upon the position and momentum coordinates. Now if we are considering the ensemble of a system along with a mental copies of the same system at that particular instant of time, so in the ensemble, the various members of the ensemble, so it will have some sort of possible microstates. So if we are talking about, so ਜਿਸ ਤਰ੍ਹਾਂ ਆਪਾਂ ਇੱਕ ਸਿਸਟਮ ਦੀ ਜਿਹੜੀ ਆ ਮਾਈਕਰੋਸਟੇਟ ਕੈਲਕੂਲੇਟ ਕੀਤੀ ਐਟ a particular instant of time, and ਜੇ ਆਪਾਂ assume ਕਰ ਲਈਏ ਕਿ there are many systems which are present in that system, this is one system, this is second, this is third, so and so there are many systems, and ਉਹ ਹਰ ਇੱਕ ਸਿਸਟਮ ਦੇ ਵਿੱਚ ਜਿਹੜੇ position and momentum coordinate ਆ ਇੱਕ same time ਦੇ ਵਿੱਚ ਜਿਹੜੀ ਆ, so they have the same microstate. So to treat the motion of these representative points along the respective trajectory, so we will define the density function. So what is this density function? It is explaining about the position and momentum of coordinate of a particular system at a particular instant of time. So similarly, if we are talking about the three-dimensional system, so this density we can represent as QPT. So 3Q, 3N, 3P, 3N. So this represents the number of representative points in that volume element. Because it is having 3 degrees of freedom, so for each position and momentum coordinate. So those point Q and P, so that is at a particular instant of time, so we can represent this density function, so that is density of Q1, Q2, Q3, and so similarly the position coordinate P3N, so they are dependent upon time, and the volume element, so this dq3n and multiplied dp3n, so this is known as the volume of confined phase space. So this volume element, so in 6n dimensional space, so that we generally represent as d omega, that is dq3n multiplied by dp3n. So this density function tells us the manner in which the members of the ensemble or the various systems which are present in the ensembles, so they are distributed over various possible microstates. So this density function it tells us that in that the members of ensemble are distributed over various possible microstates. So using this density function we can calculate the ensemble average by integrating for the whole system, and we can get, so I will not go in detail because this we will discuss in the third unit. So the ensemble average So of a given physical quantity, suppose we are talking about so a function, so f p. So the ensemble average of this function, so that is the integration of a physical parameter which is dependent upon the position and momentum coordinate. So this is our density function which will provide out the information about the various microstates, how they are changing with respect to time. So this is one is dp, other is dq over the integration of the whole confined space. So generally we carry out the integration only for the populated region, because we will cannot solve all this statistical distribution for the whole system. We will just confine a particular region and then we will calculate those integration along that populated region in order to find out the density function of that particular space. So f, this function, it is a function of time, and an ensemble is said to be stationary if it does not change with time, or it does not depend on time. ਸੋ ਜਿੰਨਾ ਚਿਰ ਤੱਕ ਤੇ ਜਿਹੜਾ ਉਹ ਫੰਕਸ਼ਨ ਆ ਉਹ ਜਿਹੜਾ ਆ ਉਹ ਟਾਈਮ ਦੇ ਨਾਲ ਉਹਦੀ ਵੈਲਿਊ ਚੇਂਜ ਹੋ ਰਹੀ ਆ. ਸੋ ਵਾਟ ਡਜ਼ ਇਟ ਮੀਨਸ? ਸੋ ਦੇਰ ਇਜ਼ ਸਮ ਸੌਰਟ ਆਫ change in microstates within that particular ensemble, and when at a time when there is no change in value of that particular microstate, so ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਆਪਾਂ ਕੀ ਕਵਾਂਗੇ ਕਿ that system or that space, it has attained the state of equilibrium, and at a state of equilibrium, so our density function, it do not no longer depend upon time. So that state is known as the equilibrium state. So at that equilibrium state, so this function, it will no longer depend on time and it is independent of time. So I hope you have grasped this concept and try to go through this concept in more detail. Then it will be easy for you to calculate the various statistical distribution. And so let us talk about now how these contact we can establish between this statistics and the thermodynamics. So in order to find the thermodynamic parameters, so contact between statistics and thermodynamics. So this will gives us the significance of microstates for a given system. Now we consider we have two subsystems. One is A1, other is A2. So the macrostates of these systems, so that is they are the function of N is representing the number of particles which are present in system A1. V is the volume, V1 is the volume of that system, and E1 is the energy of that particular system A1. And similarly for A2, so there are different number of particles, so having different volume and having different energy as compared to system A1. So the microstate of this system, so that we generally calculate with omega 1, that is dependent upon M1, V1 and E1, and the microstates of system 2, it is generally represented as omega 2, which is dependent upon the macrostates N2, V2 and E2. So the macrostates of A1, it is represented by parameter N1, V1 and E2, and the macrostates of the system, so they are represented as N2, V2 and E2. So having possible microstates omega 1 and omega 2. Now the mathematically this function omega 1 and omega 2, that is representing the microstates of A1 and A2, so they are different. So their values are different because the systems are different. So these values, so here I would like to say the microstates, so they depend upon the nature of this system. It depends upon the nature of this system कि सिस्टम किदां दा है, सिस्टम किदां दा है कि केड़ी गैस उस सिस्टम दे विच, which gas is present, either it is a boson, it is a fermion, so it will depend upon the nature of the system and its value changes. So we do believe that the thermodynamic properties of this system, so A1 and A2, so they are completely different and they can be derived from this two microstates omega 1 and omega 2. Now here what we do is, now we brought into thermal contact, so we keep these two systems combined. So when we keep these two systems into thermal contact with each other, so what does it means? So there is possibility of exchange of energy between two, so they will exchange energy. So when they will exchange energy, so if the walls of two systems, so they are conducting, so walls are conducting, and for simplicity we keep the two systems, so they are still, so what we have assumed here, we will try to compare this system one by one. So here we will apply only one condition, that the walls are conducting and there is only exchange of energy being takes place. So second, we have assumed that the walls of these two systems, so they are rigid and impenetrable. So what does it mean? So there is no exchange of N1 and N2 and there is no change in volume. So only what is being changed, so there is only changed between these two systems. So what will happen? So sum of this whole system. So now I represent this system as A naught, which is the combination of A1 plus A2. So the total energy of this system, that is sum of E1 plus E2, and that always remain constant. And if we consider that energy, so if there is no loss of energy which is being taken place, then the whole of the energy, it is being exchanged between these two systems. So the total energy, that is always conserved, and that is generally defined as E naught. So E naught represents the energy of this composite system A naught. So the energy of interaction between A1 and A2, so if there is any some sort of other interaction, so that is completely neglected. Now at a particular instant of time, the subsystem A1, it is equally likely to be in any of the omega 1 E1 microstate, while at that particular instant of time, the subsystem A2, it is equally likely to be in any of the other microstate omega 2. So what we have done is, so at a particular time, so when they are exchanging energy, the subsystem A1, it is equally likely to be in any of the omega 1 E1 microstate, and at that instant of time, the subsystem A2, it is equally likely to be in any of the microstate omega 2, that is dependent upon E2. So the composite system, it is equally likely to be in any of the omega naught. Now it is dependent upon E1 and E2 microstates. So therefore we can write it. So the microstate of the composite system at that particular instant of time, which is a function of E1 and E2, so we can write it something like this: omega 2 E2. So this we can write as omega 1 E1 and omega 2. So this we can write E naught minus E1. So we can write the microstate of this composite system. So here it is function of E1. So this microstate, it is function of E naught and E1. So let us say this is equation number 1. So this implies clearly that the microstate of the composite system, it varies with energy of any of the system. Now the question arises, at what value of variable E1 will the composite system be in equilibrium, or how far will the energy exchange takes place in order to bring the subsystem A1 and A2 in mutual equilibrium. ਉਹਨੂੰ ਕਹਿ ਰਿਹਾ ਆ ਕਿ ਕਿੰਨਾ ਚਿਰ ਜਿਹੜਾ ਆ ਕਿ ਜਦੋਂ ਆਪਾਂ ਦੋ ਸਿਸਟਮਸ ਨੂੰ ਆਪਸ ਦੇ ਵਿੱਚ ਕੰਬਾਈਨ ਕਰਤਾ ਕਿ ਕਿੰਨਾ ਚਿਰ ਤੱਕ ਜਿਹੜਾ ਆ ਉਹ એનર્ਜੀ ਐਕਸਚੇਂਜ ਜਿਹੜਾ ਆ ਉਹ ਦੋਵਾਂ ਦੇ ਵਿੱਚ ਹੁੰਦਾ ਰਹੇਗਾ ਜਦ ਤੱਕ ਜਿਹੜੇ ਆ ਉਹ ਦੋਨੇ ਮਿਊਚੁਅਲੀ ਇਕੁਇਲਿਬਰੀਅਮ ਸਟੇਟ ਦੇ ਵਿੱਚ ਨਹੀਂ ਆ ਜਾਂਦੇ। ਸੋ ਹੇਅਰ ਸਟੈਟਿਸਟਿਕਲੀ ਸਪੀਕਿੰਗ ਕਿ ਆਪਾਂ ਜਿਹੜੀ ਇਕੁਇਲਿਬਰੀਅਮ ਸਟੇਟ ਕੈਲਕੂਲੇਟ ਕਰਨੀ ਆ ਉਹ ਕਿਸ ਤਰ੍ਹਾਂ ਕਰ ਸਕਦੇ ਆ। So statistically we regard with a large number of microstates as a most probable state. So this is very important point to understand. So we regard that state as the equilibrium state, so which is having a large number of micro. It is known as the most probable state. So you can write it other way around. The most probable state of a system is the state in which system spans an overwhelmingly large fraction of time. System spans large fraction of time. So that state is known as the equilibrium state. So ਇਹਦੇ ਵਿੱਚ ਕੀ ਹੈ ਕਿ for example ਤੁਹਾਡੇ ਕੋਲ ਦੋ ਸਿਸਟਮ ਹੈਗੇ ਆ. So let us say there are 100 particles, so there are 200 particles. So ਇੱਕ ਦਾ ਟੈਂਪਰੇਚਰ 70 ਡਿਗਰੀ ਹੈ, ਇੱਕ ਦਾ ਟੈਂਪਰੇਚਰ 3 ਡਿਗਰੀ ਹੈ. ਹੁਣ ਕਿੰਨਾ ਚਿਰ ਤੱਕ ਜਿਹੜੇ ਆ ਉਹਨਾਂ ਦੇ ਵਿੱਚ એનર્ਜੀ ਐਕਸਚੇਂਜ ਹੁੰਦਾ ਰਹੇਗਾ ਕਿ ਜਦੋਂ ਸਾਡੇ ਕੋਲ ਜ਼ਿਆਦਾ ਜਿਹੜੇ ਨੰਬਰ ਆਫ ਪਾਰਟੀਕਲ ਆ, ਸੋ ਲੈਟ ਅਸ ਸੇ ਦੇ ਉਹਨਾਂ ਦੇ ਵਿੱਚ એનર્ਜੀ ਐਕਸਚੇਂਜ ਉਹਨਾਂ ਚਿਰ ਹੋ ਰਿਹਾ ਜਦ ਤੱਕ ਜਿਹੜਾ ਉਹਨਾਂ ਦਾ ਟੈਂਪਰੇਚਰ ਆ 40 ਡਿਗਰੀ ਦੇ ਉੱਤੇ ਆ ਕੇ ਸਾਡੇ ਕੋਲ ਲਗਭਗ 250 ਪਾਰਟੀਕਲ ਜਿਹੜੇ ਆ ਦੋਵਾਂ ਸਿਸਟਮ ਦੇ ਮਿਲਾ ਕੇ ਉਹਨਾਂ ਦਾ ਟੈਂਪਰੇਚਰ ਜਿਹੜਾ 40 ਡਿਗਰੀ ਤੱਕ ਉਹ ਜਿਹੜਾ ਆ ਇੱਕ ਸਟੇਬਲ ਫਾਰਮ ਦੇ ਵਿੱਚ ਫਾਰ ਅ ਲਾਰਜ ਫ੍ਰੈਕਸ਼ਨ ਆਫ ਟਾਈਮ. ਹੁਣ ਉਸ ਤੋਂ ਬਾਅਦ ਕੀ ਆ ਕਿ ਜਿਹੜੇ ਉਹ ਬਾਕੀ 50 ਪਾਰਟੀਕਲ ਰਹਿ ਗਏ ਆ ਉਹ ਵੀ ਹੌਲੀ ਹੌਲੀ ਜਿਹੜੇ ਆਪਸ 'ਚ એનર્ਜੀ ਐਕਸਚੇਂਜ ਕਰਕੇ ਆ ਜਾਣਗੇ. ਸੋ ਆਪਾਂ ਇਕੁਇਲਿਬਰੀਅਮ ਕਿੰਨਾ ਚਿਰ ਤੱਕ ਹੁੰਦਾ ਰਹੇਗਾ ਕਿ ਜਦੋਂ ਤੱਕ ਜਿਹੜੇ ਸਾਰਿਆਂ ਦਾ ਟੈਂਪਰੇਚਰ ਅਪਰੋਕਸੀਮੇਟਲੀ ਇੱਕ ਪਾਰਟਿਕੂਲਰ ਸਟੇਟ ਦੇ ਉੱਤੇ ਆ ਕੇ ਨਹੀਂ ਰੁਕ ਜਾਂਦਾ. ਸੋ ਆਪਾਂ ਇਕੁਇਲਿਬਰੀਅਮ ਸਟੇਟ ਕਿਹਨੂੰ ਕਹਿਣਾ ਆ? ਸੋ that state is known as the equilibrium state. So in which a particular composite system, it spans a large fraction of its time. So ਜਿਹੜੇ ਵੱਧ ਤੋਂ ਵੱਧ ਨੰਬਰ ਆਫ ਪਾਰਟੀਕਲ ਆ ਉਹ ਇੱਕ ਪਾਰਟਿਕੂਲਰ ਟਾਈਮ ਦੇ ਉੱਤੇ ਆ ਕੇ ਉੱਥੇ ਸਟੇਬਲ ਹੋ ਜਾਂਦੇ ਆ. ਸੋ that fraction is known as the state of equilibrium. ਹੁਣ ਸਾਡਾ ਜਿਹੜੀ ਐਗਜ਼ਾਮਪਲ ਆਪਾਂ ਲੈ ਰਹੇ ਆ ਉਹਦੀ ਗੱਲ ਕਰੀਏ. So let the equilibrium value, so let the equilibrium of E1 be E1 state कि ਜਿਹੜਾ A1 सिस्टम आ वो एक E1 बार एनर्जी ਦੇ ਉੱਤੇ ਆ ਕੇ equilibrium state ਦੇ ਉੱਤੇ ਆ ਗਿਆ. So similarly E2 ਜਿਹੜਾ ਆ it comes in the state of equilibrium when it is having energy E2 bar. So we obtained a maximizing. So if we differentiate our equation number 1, so what we get? So if we apply the Taylor expansion for this equation 1, curly omega 1 which is dependent upon E1, so with respect to E1, so E1 it is dependent upon E1 bar into omega 2 E2 bar plus omega 1 E1 bar derivative of the other function that is omega 2 E2 bar with respect to E2. So multiply by curly E2 over curly E1, so that is equal to 0. So this is our most probable state. So that is the state of, this is a constant value because omega naught and a naught they are constant and derivative of a constant, so it is equal to 0. So we get constant on right hand side. ਹੁਣ ਸਾਡੇ ਕੋਲ E1 plus E2 ਜਿਹੜਾ ਆ, so that is E naught, again it is a constant value. So if you take the derivative with respect to E1, So this becomes curly E2 over curly E1. So that is equal to 0. So curly E2 over curly E1, that becomes minus 1. So if we put the value of this curly E2 over curly E1, so in this equation, so what we get is, we get omega 2 E2 bar curly omega 1 E1 over curly E1. So only 5 minutes we will talk more. So E1, that is at E1 bar. So omega 1 goes to the right hand side. So this equation becomes so E2 value at a energy E2 bar. Now we can write this equation as omega 1 E1 curly omega 1 E1 over curly E1. So that is equal to 1 over omega 2 E2 curly omega 2 E2 over curly E2. So this is energy at E2 bar. So this is energy at E1 bar. So we can write as curly log of omega, because when we take the derivative of log omega, so this is the same equation which we will get over curly E1. So that is equal to curly log of omega 2 over curly E2. So thus our system, it comes in the state of equilibrium, and when this will come in the state of equilibrium, so the condition is beta 1 is equal to beta 2. Now what is this beta? So this we will generally represent with the term, so that is curly log of omega, which is function of NV and E only, over curly E. So if we are considered that, so there is only exchange of energy being takes place. So when these two physical parameters, so this is for the system A1, this is for the system A2. So when two physical systems, so they are brought into contact with each other, so they exchange their energy which is being taken place between these two systems. So this exchange of energy, it continues until the equilibrium between this system A1 and A2 comes out. So once they reach out the value at a particular energy value, so there is no further exchange of energy which is being taken place between these systems. So when there is no further exchange which is happening between these systems, then that state is known as the state of equilibrium. And this state of equilibrium, so that happens at a particular instant, so which we will generally define. So when the value of beta 1 of one system, it comes out to be equal to the beta 2 of this second system. So this, from here we will continue our next lecture, and we will drive the relation. So we will drive the relation between beta and temperature T. So from that, once we have derived the relation between this beta and T, from that we can derive the relation between microstate and thermodynamic parameter. So thermodynamic parameter, that is our macrostate. So the main important study of statistical mechanics is to establish the relation between microstate and macrostate. So once we are able to establish a particular relation between these two parameters, from that it is easy for us to calculate the various physical parameters of that particular system, what is happening in that system, and so we can discuss all sorts of thermodynamic parameters from those microstates. So I hope you have understand this lecture. So if you have any queries, you can ask me, you can WhatsApp me, or you can check these